Hey everybody, Rob Maurer here, and today we are joined by James Douma to talk about Tesla's approach on autonomous driving, specifically on neural networks. James has a ton of knowledge on this space. He was actually on the podcast back in 2018, for those of you that have listened for a long time. And today we're continuing some of those conversations, learning a little bit more about Tesla's strategy here. So this is a multi-part conversation. Make sure to subscribe for part 2. And with that, we'll jump right in.
I've been doing neural networks for a really long time, although it hasn't been a job. And lately it's turned into an investing thesis. So for the last decade or so, I've been a full-time investor. I just invest my own portfolio. And my MO is I look for companies where the technology difference in their approach is something which is a good fit for my background and expertise. And then I tend to do deep dives on them. And so Tesla is actually my deep learning company. It's 10 years ago, before I got into Tesla, when I was looking for companies that would be able to keep using, make good use of computation as it continues to expand. I know you probably know that Moore's law is, it's been something that it keeps going, and people inside the field think it's going to die every year. It's I understand that there's this joke in the printing business about how the second book Gutenberg printed was about how the publishing industry was doomed. And Moore's law is kind of like that. And it's, every year we come up with a reason why it's not going to work. So when I started looking at the thesis of like, well, what if it doesn't end? What happens? You only need your spreadsheet to load so fast, and video games can only use like so much horsepower, although they're pretty good at syncing it. Like, if we have 1,000 times or 1,000,000 times more horsepower, who can use it? And machine learning models are the obvious place to put that, right? They're this total bottomless pit of computation that you can throw at the problem, because they scale and they just keep getting better. And as long as there's, if the computation keeps getting cheaper and the data sets keep getting better, machine learning can use it. When I started looking around at who could really use that stuff, strangely, the people you really think of, the Facebooks and the Apples and the Amazons and whatnot, it makes a difference to their business and they need to stay on top of it. But it doesn't 10x their business. Like, no, not very many people are in that space. So when Elon made a big bet on using deep learning for FSD, like, that's a 10x to me. So I got really interested and I really dove deep on it. Along the way, I encountered Very Green. Went on
Green the only on Twitter, right?
Yeah, Green the only on Twitter. He was, doing his thing with Teslas and pulling the code out and going over it and trying to understand everything that was going on. And he was running across these neural networks. I begged him to get copies of this stuff. And then after a while, it took some time, but we figured out how to take them apart and figure out what the shape of the thing was. And there's a lot of stuff that we can't see. But in those early networks, I could get a sense of what was going on, what tools they were using, what kinds of approaches that they were using, and sort of collaborating with Green. We got a sense of how the fleet learning thing worked, how they were pushing, what kinds of information they were pulling. And so that was a fun investigation. I bought my first Model S in 2015 because I wanted autopilot. Like, that was the reason that I got the car. In fact, I have this story about, I went down to the factory. We took the tour. I got the car. I turned on autopilot as soon as I exited the factory parking lot, and I had it drive me all the way back to San Francisco. And in those days, autopilot was pretty sketchy. So we use it a lot. I think I must be at about 90,000 autopilot miles now, and I've driven every version, and we've used them. I think I've driven autopilot in 47 of 50 states and most of the provinces of Canada. So, so that was a big part of trying to understand what autopilot was doing. Yeah. And having a deep learning background and looking at what was state in the art for a lot of the basic techniques that go into it, it was a way to kind of balance those two off of one another also. So from time to time, Green will get his hands on another neural network and I'll get to take a crack at it. And when Hardware 3 came out, that was actually a big plus for us in a strange way, because the neural networks before hardware 3 were running on a GPU, and it's pretty hard to figure out what's going inside a GPU. The code is very complicated. But when Tesla made the neural network processor, one of its benefits is that it really simplifies the use of neural networks, and it's very easy to take apart the code in that. So we started to get a very clear understanding of the structure of neural networks that run on that processor. Now, not all the neural networks that run in a Tesla run on that processor. The really heavy ones do, and the ones that are very vision focused. But one of the characteristics of that processor is its core processing capability are these very big multipliers. It can take a 96 by 96 square array of numbers and multiply it by another 96 by 96 array. That's doing so basically 10,000 operations, and then do an accumulate, and it can do that every clock. And it does 2 billion clocks per second. And so that's where you get to these sort of insanely huge numbers of math operations that they can do. But if you want to multiply a 10 by 10 array matrix, like, the efficiency is terrible. It's horrible at that kind of stuff. And there are operations that you need to do inside neural networks that aren't at these, giant, homogeneous blobs of data. And for those kinds of things, there are other processors. The FSD chip's got 12 ARM CPUs, and it's got a big GPU with a bunch, and they do pre-processing. They have a vision processor and so forth, right? So anyway.
So I'd love to talk a little bit more about the hardware. Let's maybe set the stage in terms of just like, we were talking earlier this week about Andre Karpathy's interview on the Robot Brains podcast. He was talking about deep learning, neural networks. I'd love to just get you to briefly explain, as brief as we can be, where we're starting from here. Deep learning, neural networks, how are they working? How is Tesla utilizing them?
Okay, so vision is an old business. People have been trying to use computers to do stuff with images for a really long time. And the idea of writing software that could understand what's in a photograph has been a long-standing computational challenge. And it was a computational challenge that the world made essentially zero progress on until arguably like December 2012, which is when the first ImageNet, where a deep learning neural network was brought to it was brought to bear on the set of problems which ImageNet had challenged itself with. And you got this rather discontinuous improvement in the performance of neural network on understanding of vision software on understanding what's inside a photograph. And then year after year, it continued this. Like, people kept reapplying these deep learning neural networks to the problem, and they got a rather complete. The rate of progress had been about like this, and then neural networks came on, and suddenly the rate of progress was like this. So here we are, 9 years later, and in a lot of the things which we hadn't been able to make any traction on in computer science for a really long time, they're not totally in the solved band, but they're very close to the solved band. There's this canonical, and Andre mentioned it in that interview. There's the canonical problem of like, can you write a computer program that can tell a picture of a dog from a picture of a cat, right? And literally up until around 2012, that was sort of shorthand for this impossible thing that we know is doable, but nobody has any clue how to actually make it work. I think Andre said nobody can write that program. And people tried writing that program. We tried all kinds of techniques for doing that. And yet, we could do that then. And telling dogs from cats, that's solved the problem. I mean, that literally, it's a thing a high school student can do on a laptop now, right? And it was completely impossible 10 years ago. So that's what neural networks have basically brought to this. I mean, they're good at lots of different kinds of problems. They started, vision was one of the big things that they cracked early. And they continue to be the premier way of understanding a photo kind of in the way a human being does. A human being looks at a photo and we don't see a blob of pixels. We don't see slabs of color, right? We see tree, beach scene. We see a picture of the moon. That's what we see, right? And so neural networks are giving computers the ability to do that same thing, to see the pattern in the pixels that represents something that the picture is trying to capture. And so there's a great opportunity in self-driving cars for using cameras to understand the scene. And you literally can't do that without neural networks today. Everybody who uses cameras on self-driving vehicles is using neural networks. Most people are using a lot of stuff besides cameras. The self-driving cars is a problem that was worked on with great intensity long before neural networks matured. And there was big investments that had been made by some rather large organizations in trying to crack that problem. So they had big investments that were more based on, I mean, they used vision, but they used kind of classical vision, pre-neural network vision. And they also had these very sophisticated sensors that they would put on. And the job of the sensors was to bridge the gap between what you could understand with the cameras and what you needed to understand to drive the car. So neural networks change that equation in a pretty significant way because they present the possibility, and at this point, the very strong likelihood that the camera itself is going to be sufficient, right? That you're not going to need other things to supplement the weaknesses of your cameras because the cameras are going to be adequate to doing the job. And so Tesla has made that bet. So how do they work? So listening to Andre's description, I think, is worthwhile. This is it. I actually kind of feel like my explanation is a little bit better because I have to explain this to my mom over and over, right? And I get the impression
actually answered that question.
that Andre doesn't actually explain it to his mom as much, or maybe his mom is a CS grad and she can deal with the lingo and it works better. But the way that I usually talk about this is neural networks are they're graph networks where the computation is it's a consequence of lots of little operations that individually don't seem like they're going to amount to much. But when you get the numbers of them, when you do large enough blobs of these numbers, you get computation that is not obviously something that you can get to just looking at the little operations. So the core thing that Tesla uses and the core thing that's mainly used in neural networks these days is a convolutional operator. We have neurons that do what we call convolutions. And convolution, what a neuron does, basically, a neural network neuron is a node that has some set of inputs and it applies some process to them and it generates one output. So a neuron in a neural network, it could have a very small number of inputs. It could have a lot of inputs. It's pretty common for neurons in neural networks to have between a few hundred and a few thousand inputs. For each one of the inputs,
like coming from different sensors, you're saying there? Are they looking at like just an array of pixels, or what do you mean by an input?
So neural networks, they're typically built in layers, and the input layer is always whatever you're putting into the neural network. So the neural inputs, in the case of a camera, you have an image that's, if it's a megapixel image, it's 1,000 by 1,000 pixels. And of course, those pixels to a computer are just numbers, right? You might have red, green, and blue channels, and you have an intensity, which will go from like 0 to whatever the maximum is. Like if they're 3 bytes from 0 to 255 for each of red, green, and blue. And so those are 3 channels, 3 colored channels. And you'd have, however many wide by however many vertically. That's the input to the first layer of a camera network. Subsequent layers take as their input the output from the previous layer. So the very first layer's input is whatever your signal is, which for voice recognition would be the sound of a voice. For a text generator, it's the text that comes in. And for an image processing network, it's the raw pixel values of the image that are coming in.
For all pixels, or all text, or all voice, all hit that first layer of the neural network.
Right.
Okay.
So for instance, the first layer convolutions, you've got neurons that are basically looking at small fields. They're so a classic size for a neural network in an inception network, the first layer would be a 7 by 7 input field. So a neuron would take a 7 by 7 block of adjacent pixels in an image, and those would be the inputs to that one neuron. Now, if you have, say, 1,000 by 1,000 image coming in, you need 1,000 approximately. You need 1,000 minus 7 neurons by 1,000 minus 7 neurons, because the first one gets the first 7 pixels by 7, and then the next neuron over in that row of neurons in the second layer looks at, pixel, instead of pixel 0 through pixel 6, it's looking at pixel 1 through pixel 7, and then 7 rows of that, and so on as you work your way across. Right. Yeah. So that would be what's called a stride of 1, where you have where you move over by 1 pixel on each layer. So all of these are architectural elements that the designer can decide on. They can decide what the stride is going to be. They can decide if they want the neuron to be a 7 by 7 or a 5 by 5 or 3 by 3 at the first layer. So on that first layer, each one of the neurons that has a receptive field has some set of weights that it applies to, and then those weights, so for instance, let's talk about a 2 by 2 grid, just to have a really simple example, right? Okay, and if your weights were 0, 1, 2, 3, and you've got some pixels coming in, and say all the pixels, it's a white field, they're 1, 1, 1, 1. So those 4 weights get applied to those 4 incoming pixels. So the outputs of those would be 0, the 0 pixel, to the 1, the 0 weight applied to the 1 pixel, to the white 1 pixel, and the next one over, the pixel is also white, but the weight there is 1. So the multiplication of those 2 gives you 1, and then 2 and 3 for the others. So then that neuron would sum together those 4, the results of those 4 multiplications, and then it applies a nonlinearity, which is basically, it has a threshold. If you exceed that threshold, you get an output. And if you don't exceed that threshold, you don't. Now, what this neuron is doing is, this neuron, it's looking for a pattern in those 4 pixels or those 7 by 7 pixels. Now, that pattern could be an edge, a diagonal edge, a horizontal edge. It could be a gradient from light to darkness. It could be looking for a red field or looking for a gray field. It could be looking for almost anything that could kind of uniquely appear inside that thing. And what you get is a degree of match. The neuron, by applying those weights to that chunk of field, it's basically saying, how close is this field to this thing I'm looking for? And if it crosses a threshold, you get an output. And if it doesn't cross that threshold, you don't get the output. So that initial 7 by 7 field in the top corner of a pixel, I just described one neuron, but there would be many layers for many features. So that one field, it'd have one neuron for, say, the diagonal edge that it's looking for, but it would have another neuron looking at the same field that might be looking for horizontal edges or a different diagonal edge. So you can pick some number of these input channels, it would be called, in the second layer. And each one of them is looking for a unique feature. Now, you look for that same set of features in every single, say, 7 by 7 grid across the entire image. So for instance, you might have, say, 128 channels in that second layer. So there's 128 unique features that you're looking for in every 7 by 7 block of pixels all the way across this image.
So like 128 neurons, basically, is that equivalent to that?
So you'd have a stack of them, right? So you could think of, if you have the image here, you can think of that first kernel as essentially being replicated back and forth all the way across the image. So if that first one is, I'm looking for diagonal lines, it checks for diagonal lines here and here all the way horizontally, and then in a grid all the way through. And it will give you a positive for every location in the image where there's a diagonal edge. Does that make sense?
Yeah.
So say you have diagonal edge, horizontal edge, a different diagonal edge, color gradings of a bunch of different things. You have 128 unique features that you can look for. The third layer takes those as inputs. And it also has a field. It looks at multiple neurons across a space. So for instance, it could say something like, well, if there was this line and there was this line, and in the next pixel over, I had a gradation, and so on and so forth, it can have a higher level feature. So the second layer, its outputs are essentially triggers on composites of the second layer's features. So it could take any of those 128 unique features that was getting looked for across its entire input field, and it can have a weight that says, I will activate if I see a particular combination of these. And it's not a simple, it doesn't have to be a perfect match. Because of this, because we're multiplying these weights and applying a threshold, anything that exceeds the threshold will get a different degree of firing, right? So you've got below a certain threshold, it's definitely not there. And above a certain threshold, it's there to varying degrees. And you can have sort of a scale of those degrees. So it's not completely black and white, even though you have a nonlinearity. So one way that this gets described is you have these very low level visual features in the first layer. And the second layer is combinations of those features. And the third layer is combinations of those features. And the fourth layer is combinations of the third layer's features. So you're working up what can be described as layers of abstraction. At the bottom, toward the bottom of the network, and there can be many of these layers. There are some kinds of neural networks where they have 100 layers. ResNets that are 100 layers deep occur. Those are not the kind of networks that Tesla uses, but there are networks that are super deep. And Tesla's Cameron networks, it's pretty common to see 20 or 30, 40, 50 layers. So you don't have to, it doesn't take very many layers to work your way up to very high levels of abstraction. But rather than try to have very large numbers of kernels in a small number of layers, the way the networks tend to get built is you'll start with, so for instance, in one of Tesla's networks, they might have 8 kernels in the first layer. And then they might have 16 in the second layer, and they might have 32 in the third layer. And there's another thing that tends to happen in these are convolutional neural networks. Another thing that happens in convolutional neural networks is that the data gets a chance to consolidate as you work your way up, because the first neurons, they have a receptive field that has some width, right? But because the second layer of neurons is the outputs of those, it's effectively seeing more of the input image. So its output can be affected by a wider range of the input. After you work your way up a certain number of layers, you've gotten to a point where even the neurons in the center of the grid have an opportunity to be influenced by neurons all the way at the edge of the pixels. And above that, it's just mixing, right? You no longer need the receptive field to get bigger. So one of the things you can do is you can reduce the width of the image at each stage as you work your way up. So you might start with, say, 1,000 by 1,000, and you do a layer at 1,000 by 1,000. Maybe you do 2 layers at 1,000 by 1,000, and then you can narrow it to 512 by 512 by getting rid of half of the stuff. Then you do more layers at 512 by 512, and then you'll narrow it down to 256 and so on. So as you work your way up this stack, what happens is the number of channels, the number of kernels you apply at any location tends to increase. And the width of the field, in terms of the number of pixels horizontally and vertically, gets smaller and smaller. So by the time you get into the center of the network, you've got these sort of cubes of values that are coming out, because you've got an XY coordinate, which roughly corresponds to a zone in the image. And then you'll have a certain number of kernels for each one of those. In the recent networks, it's not quite the same, but in AP, they had layers that would have 2,000 or 4,000 kernels on each one of these inputs. So at the beginning, when you say, man, how do I understand an image if I only have 128 unique features I can look at in the first layer, right? But when you start to get into the middle and you're looking at thousands of combinations, like, your first layer might have, 16 kernels or 32 kernels for the input field, but then the next one is 64 kernels. So you've got 64 combinations of 32 basic ones. So the next one might be 128. So now you've got 128 combinations of 64 combinations of 32. So you don't have to get very far up that stack before the combinatoric space of possibilities just explodes, right? So the neural network in principle can mix all of this information working its way up. And this is intentional, because when we build a neural network, what we start with in the architecture is we want an architecture that definitely has the potential to have at least one configuration in that mix of all of those possibilities that can solve our problem. And then the trick is figuring out how to set the weight so that it does do the thing we want. So for instance, I'm trying to tell cats from dogs, and I've got my 10 layers of my convolutional neural network. And at the output, I just have 2 neurons. One of them is the cat neuron. One of them is the dog neuron, right? I give it a picture of a cat. I start out with random settings for all the weights, like all of those numbers I'm multiplying the weights.
So real quick on the weights,
Mm-hmm.
So Andre in his talk said like ImageNet, for example, had 60 million weights or knobs.
Right.
He called them. Is that on each sort of neuron that's firing or not firing? Has the 60 million weights on it, or is that
No.
across the
So
entire
that's the
like
sum of all
net?
the neurons. So
Okay.
I think they had on the order of 200,000 neurons in those 60 million weights. So,
Okay.
60 million divided by 200,000, that's the average number of weights you had per neuron in the entire network.
Okay.
Um, so,
So each neuron
the,
might have like a couple hundred knobs, essentially, or knobs or weights.
yeah, so typically it would
Okay.
be on the order of a couple hundred. It could be significantly larger. It could be significantly lower. So for instance, if in the middle of the stack, you have 2048 channels, you have 2K kernels coming out of layer X, and now you're on layer X plus one. If layer X plus one has an input field of 3 by 3, and you have 2K kernels in the previous layer for each one of those input channels, and you have 2000 by 9 values going into each neuron in the next layer up, right? So in that case, it would be like 18,000 inputs. So that would be kind of in the middle of a deep network where you're doing a lot of processing. You're really mixing a lot of stuff. In input layers, you tend to have less. And the simple reason for that is that typically you want to shrink the input field relatively quickly because it's computationally inefficient to operate in these very big fields. So you do smaller numbers of kernels and you aggressively try to shrink the field so that you can have more channels, more distinct kernels, and each one of them can be influenced by a really large portion of the input image.
Is a fair way to describe a kernel would that be like sort of a capsule of information of the results of the previous layer? Is that correct?
So a way of thinking of a kernel is a thing that's looking for a particular feature. So it's one neuron.
So it's like if this is diagonal, yes, no. Yeah. That's like a kernel of information. Right. Combined with all the other outputs of all the other neurons.
So if you have the 7 by 7 input field and I have a set of weights, say for instance, imagine, I've got a grid of 7 by 7 and it's all zeros and I just have a line of ones up the corner, right? Well, that'll detect a diagonal line if it's right up the corner. Because if I look at a field that doesn't tend to have a diagonal line where these weights don't matter very much and these weights do matter, then when I do my multiplications and additions, it's not going to exceed the threshold necessary to fire. So it's not difficult to visualize like approximately what the weights need to be. Actually, what you want to do in that is you want the average weight to be 0, right? So I've got 49 weights in my 7 by 7 field, and I have one set of the diagonal ones that run up, say, from corner to corner across the middle of the image. They might be some significant positive value, and all the rest are a slight negative value, so that the field overall adds up to 0. So if you're just looking at some constant color, the output of the neuron is 0, right? But if to any degree there's more stuff happening along that diagonal line than there is in the rest of the image, there will be a tendency to fire. And then once I can pick the threshold, like how much of that do I need to see before I want this feature to activate? So that's an example of an input field, a kernel, which is just looking for a diagonal line. Call it a diagonal line kernel. Well, you would have exactly the same weights the next kernel over and so on, right? Because I'm going to take this kernel and I'm going to use it. The way the neural network is actually architected, the adjacent kernels all have exactly the same weights, but I have a significant number of those kernels, perhaps. Like if I have a 7 by 7 input field and I have 16 kernels, I have 7 by 7 weights that I'm applying all through the entire image. And I've got 16 sets of those. So for every pixel in the output layer, I have 16 distinct features, each one of which has a 7 by 7 field. But it's the same set of features as I work my way across the image. So I only have to come up with one good set of weights for detecting diagonal lines. A diagonal line is the same, whether it's in the top right corner or the bottom left corner of the image. So we use the same kernel all the way across the image. But we have to choose a small finite set of features that we're going to use. And an interesting thing is, like, as a human being, people tend to choose these highly distinctive things. Like I'm using a diagonal line as an example. A neural network would never do that because it's a waste of a feature to have a whole feature dedicated to just diagonal lines. Instead, what neural network, because they figure this stuff out on their own. There's a process I'm going to describe for how they learn.
That's what this sounds. It sounds like so hard to figure out what you would want to extract from 7 pixels that would be valuable at the end state. You know, that's where it's like, this is just kind of mind blowing.
Yeah, and when humans have built these things by hand before, right? Mobileye started out hand engineering their kernels and their vision engine. So using convolutional kernels predates neural networks, right? People used to design these things by hand when they were trying to hand write the dog and cat program, or much more simply, the handwritten digit was the original NMIST task, where at Jan LeCun's lab, they got hired by the U.S. Postal Service to create a neural network that could read handwritten, zip codes off of letters. That's why we have zip codes, because reading handwriting was pointless. But if we could read the zip code, we could figure out where the letter went, right? But people write, the digit 7 lots of different ways, all these sizes and whatnot. So, there was this challenge, which was, if I just have 10 digits, can I build a neural network to do that? And LeCun's group did figure that out. They figured that out in, I think, 2007. It was working pretty well. And that was one of the first they tried a couple of different ways of doing it, but the first version that was successful was a convolutional neural network at a very small number of layers, because back then there wasn't that much computational power, right? They had a relatively small database to train with. And it's still, MNIST is a thing, like people make MNIST, you can train MNIST in a browser using JavaScript now, because computers are so much faster than they used to be. And it's a thing that, anybody who takes any neural network course, a high school course, or you do a tutorial online or something, they'll hit you with that. And anybody with like a couple of hours of work can basically crack MNIST now, right? Whereas back in 2007, it was a real challenge, and it took a while to get that. Now we know how to do it. We've got all of these existence proofs for the tweaks that you have to do it. But LeCun's group, they had to painstakingly try all these different variations on, how you could arrange the neurons, and how many layers do you need, and what's the right size of a kernel, and, how little can I get away with and still solve the problem, was a big challenge. Today, you can, not only can you solve MNIST, you can totally brute force overload it, that it's not, it's much less of a challenge than it used to be, despite the fact that besides the fact that we know exactly how to do it, we can also throw 100,000 times as much computation at it if we want to, right? So, so things have changed. The way that works, so once I've got the shape of my neural network, I've decided, what my input fields are going to be and how many layers I have and how many neurons I'm going to put in each one of those. Initially, you just start with random weights. You have to start someplace. So you program in a set of random weights. Typically, it's got like a bell curve distribution, statistical distribution, and they average to 0, because the point is you want it to be on the cusp where it could go left or it could go right or whatever. So then I take my completely random network and I showed a picture of a cat, and I get a guess at the output of it. Maybe it's the output is, I think that's 70% cat, 30% dog. You get a probability, right? You say the correct answer is 100% cat. Now, the thing about a neural network, and this is really key, is that the function has to be what we call differentiable, which is to say that everything, all the transitions that occur as you work your way through it are smooth. Like they used to always, today we use these ReLUs as nonlinearities, but they used to use a sigmoid function. And the point of a sigmoid was that you knew which way was downhill at any given point. It's differentiable. It doesn't have any sharp breaks in it where there's a point where you're not quite sure, am I going this way or am I going that way? There's always a slope. If there's a slope on every single weight, on every single layer, all the way through, then you can do this trick called back propagation, which is if the correct answer was 100% cat and what the network gave me was 70% cat, because there's smooth variation of all of the influences all the way through the network, I can walk back from the end all the way through, and I can determine for every single one of the weights in my network. So if it was ImageNet, for all 60 million of those knobs, 60 million of those weights, I can say exactly how much it would have to change to become dog. Now, I don't flip all the weights so that they would say dog. What I do is I say, if I would have to change this X much to become dog, I'm going to move it just a little in the dog direction. Maybe I'll move it 1% in the dog direction. And you do that for every single one of those weights. Now, this sounds complicated, but it's with matrix math, it's a trivial computation. You need, like an FSD chip type thing to do it because it's a big chunk of matrix math, but it's stupidly simple matrix math, right? I mean, it's literally, it's an equation that's got like 4 terms or something. It's really easy to write out. So the thing is, you just do this big matrix math thing, and it tells you exactly how much every single weight contributed to the failure to get 100% cat. And then you tweak it 1% in the right direction. And then you give it the next picture. And that one's a dog, and it gives you some guess about dog. So all the cat pictures get tweaked slightly toward cat, and all the dog pictures get tweaked very slightly toward dog. And the thing is, you run 1,000 pictures of cats and dogs through it, and it's got cat and dog down. It's amazing. It just freaking works.
It's so amazing. Like, this is just incredible.
I think it's not well appreciated. It's funny, that back in the early 80s, neural networks first started working. So neural networks, they were called perceptrons back in the 60s when people first came up with them. And they were just thinking about, well, the point was they were modeled on the human visual cortex, which is a part of the brain, or the animal visual cortex. Humans and animals, mammals, they have visual cortexes. The structures are kind of similar. Different, species have different numbers of layers, and there's a little bit of variation, but the general idea of how they work is pretty straightforward. And that structure's kind of been known for a while. So perceptron was one of the things that was kind of inspired by this, like maybe this is a way to get, to build systems that can learn. We had this idea a long time ago. The thing is, it does definitely have this free lunch kind of feel to it, right? Like, I think there was always this suspicion that it couldn't be that easy and it wouldn't work. And sure enough, like back in the 60s, there was a lot of debate about whether this thing was going to work. And the consensus that people who, there were like, you couldn't, like, you would have had to solve it on paper or something. I mean, they just didn't have computers back in the 60s that could tackle this problem. So it was a theoretical exercise. And it was more or less concluded after, some theoretical studies. In fact, Marvin Minsky wrote a famous paper where he proved certain limitations of single layer perceptrons. And the field kind of went, oh yeah, they must not work. And they just sort of dropped it. And then in the 80s, it came back, the idea, because in the 80s, we finally had personal computers. They could sit on your desk. You could do little tiny networks. And people started playing with them on super, super toy problems, and they could get them to work. They could get back propagation to work. The problem was they couldn't get them to work. I mean, the promise was not to use neural networks to solve problems that we could already solve with symbolic math, right? The fact that they worked at all was amazing, but they weren't solving problems that were interesting in the sense that you couldn't solve them other ways. And they're hideously inefficient because they take all these operations. So the fact that they learned wasn't really great. And then the other problem was, it turns out that there's a stability problem with neural networks as you add layers. You have to, when I said before that, you only want to move maybe 1% in the direction of cat when you have something. And the reason for that is because you want the network to converge to the right answer stably. And if that step is too large, they become unstable and they don't converge and you don't get good results. Well, if you don't have very much computation, the tendency is to want to take big steps, right? Because you don't want to have to do this a million times. And that was a problem that we were just stuck with back in the 80s. We couldn't do it. And so once again, the field kind of looked at this stuff and they said, it's neat. It's cool that it can do this stuff, but obviously it can't solve any useful problems, right? So we're just not going to do that. And the thing is, before the field decided that there was no hope, a lot of people put a lot of money and effort into it. And they kind of felt like, Pons and Fleischmann with the cold fusion stuff, right? It's like neural networks became persona non grata, and you couldn't get a neural network paper published for a long time because it was kind of like astrology. Yeah. Like, they thought, oh, you're one of those people that won't give up, sort of things. And so one of the reasons why Jan LeCun and Jeff Hinton and I'm gonna flub the third name. Oh man. Anyway, we had a core of people who didn't give up, who really stuck with it, and eventually computation caught up to what was necessary to actually get the process to perform. And so you just had these few guys that were out in the wilderness sticking with it, right? And eventually the data sets and the computation caught up to it, and the thing started working. But because we had this window of time, like between 2007 and 2012, there was plenty of evidence that it worked. There was nobody who would listen to you if you would tell them it was working. If you weren't one of the people that was working in one of these labs, like you could know it was working and you were making really good progress, but you weren't getting there. But then in 2012, Hinton and showed up at ImageNet, and they just completely crushed, like he assembled armies of the vision world. I mean, like it was a humiliating difference. They made more progress. Like they're grad student with a desktop PC and 2 GPUs in it made more progress in 1 year than I think the whole field had made in a decade or 15 years or something like that. And that was the point where the field as a whole sort of looked at this and said, yeah, maybe we'll look at it. maybe there's some merit to this idea. Yeah. And I think Karpathy said in his talk, it went from, maybe there were 2 papers on neural networks at a conference on vision to maybe there were 2 papers that weren't on neural networks at a conference. Right. Like it was that quick in the academic space because the evidence was so clear that there was, but even so, there was this sense in and certainly in academia, but generally experts in the field had looked at this thing and they're like, they remembered, like people have been around for a while. They remember what happened in the 80s where like, for 2 years there, it looked really good. And then boom, nothing after that. Right. And they were kind of waiting for that other shoe to drop for a while. So 2013, it was at the end of 2012 when this happened. 2013 rolls around, 2014 rolls around. And they're still getting better and better and better. But as you can imagine, it took until like 2017 before people started really saying, I think maybe this time it's going to keep going, right? Before that kind of became, now the consensus is it's going to keep going. And now the question is it really going to keep going? Like, is it going to be like Moore's law and keep going for 30 years? Or is it going to start to taper because we're getting into diminishing returns? Like there's that tension about how much to believe in this and whatnot. And the OpenAI has done a great service in the stuff that they've done. And they have been working super hard to push the envelope to go to really big systems and really big networks and really big data sets to understand if this technology scales. And the answer overwhelmingly is, oh man, does it scale? It scales like nobody's business. Like you can throw all the data you want into it and it gets better. You can make the network as big as you want and it gets better. You can train it for longer. You can use bigger computers. Like it just scales. Like everything you throw at it makes it scale better. So I think the smart money right now is on it's going to scale, right? Even though there's still
probably why Andre, that's probably why Andre made a point of saying that, like he doesn't see an upper limit on what is feasible here. It's really about, the network size, the data set, the compute, and then that's kind of the limit, as those all scale.
Yeah, and I think the point, he also made the point that, it used to be the problem was the algorithms, right? We had computers but it doesn't matter, like I said, it doesn't matter, how fast you open your spreadsheet. There are things that there's just no, you can only run like a tree search algorithm so fast, right? There's only so big a tree. And it doesn't matter if you run it 10 times faster, you don't need that answer. But with a neural network, you can make the tree, 10 times, 1,000 times bigger, and you get a better result. And so now we're, there's a balance between, you don't want to just throw data centers into this gaping abyss of computation because the solution space is really astronomically large. When they cracked Go, which is a big surprise, right? People were fond of pointing out that there are more Go positions than there are atoms in the universe, right? It doesn't look like a very big board, but if you wanted to brute force search it, like that's, in fact, I think it's like 10 to the 30 times as many atoms as there are in the universe, right? It's just like, you cannot brute force this problem. And neural networks are typically like that. Like if you wanted to try all the possible combinations of 60 million weights, like if you were just going to brute force that ImageNet network, you have no hope. You can't make a dent on it, right? The fact that backpropagation consistently as a technique, it consistently migrates you from a worse network to a better network. And it's a matter of being patient and giving it the right data and it will just continue to get better. And what we're learning is how big a step you can take, and how, what is the smallest neural network that can really do this? Because if you got a neural network that's got 10 times as many weights as you need, well, then you could solve this problem 10 times faster if you just knew what the smaller network is. So we get smarter at figuring out the right shape for networks. What's the minimal shape that lets me find the result relatively quickly? And we get a lot smarter about, like, how big a step can I take and still be guaranteed to converge on a result? So these algorithmic improvements, they also are, computers get faster, the data sets get bigger. We build more specialized hardware for doing this stuff. But even more important than that is that year after year, the techniques themselves are 10%, 20%, 30% better every year, right? On 3 or 4 different dimensions. So we have all of these, what seem like pretty open-ended opportunities to continue improving these things. And like I said, I think at this point, the smart money is on. It's going to be a really long time before we start getting into diminishing returns. We're already in diminishing returns in terms of, how much can I get inside one particular envelope, right? But we're not in diminishing returns in terms of, like, how all of these things work together to increase the total power of the technique against the set of problems that I'm trying to solve.
So I just had a question, now I lost it. Is one of the issues with, like we were talking about Go, is one of the issues with a driving situation the amount of time that you need to run the neural network to make a decision obviously is limited, because you can't just sit there and think about what move you're going to make. You have to constantly be doing that at, up to 80 miles an hour or something like that. Is that one of the challenges with FSD that's unique?
It's an economics challenge in the sense that, say, for instance, you feel like you need 100 millisecond latency between visual input and making a solid driving decision. So for a given investment with a given technology, you can only do so much computation. And so that sets an upper bound on how big a neural network that you can have. So when we talked about those 60 million weights in the ImageNet network, each one of those is a mathematical multiply accumulate operation. So you have to do 60 million multiply accumulates. So you have your image, you do your 60 million multiply accumulates, and you get your answer. So how fast can your computer do that? That's your latency. If you make the computer faster, you can shorten that window. Or if you make the network smaller, you can shorten that window too. That's the other thing. So when they were still on AP2, there was a significant trade-off there, right? You could only make a neural network so big because you needed to get inside a certain window. And the size of that network for the GPU, the GP106 GPU that we had in the AP2 and AP2.5 hardware, or the hardware 2 and hardware 2.5, that it was definitely a constraint. I think especially, toward the end of that program, before hardware 3 rolled out, I got the impression, looking at the neural networks, that they were kind of constrained. Like, they would like to go bigger. You could see that they had expanded the neural networks up to some point, and now they were doing things where they were doing trade-offs between internal layers, like, I need more computation in this layer, I'll take it away from that layer. It wasn't just like, go bigger, right? And when they got to hardware 3, they were freed from all those constraints. They suddenly had dramatically more capability. You can't immediately go to a 10x bigger network, because it takes 10 times as much training time, and they were already spending a lot of it. You have to train these things, so in a sense, if Tesla pops out a new neural network every couple of weeks, as they're doing right now, those neural networks, they take 3 solid days to train on a big data center, right? And you don't train just one, you train several of them and you test them or whatnot. So you can definitely get to a point where, like, we don't have enough data centers to just like brute force this problem. We have to kind of finesse it. And one of the ways of finessing it is, well, how big a network do I really need? I'm not going to make it 10 times. I'm not going to make it gratuitously big. I can't afford that. So, but they're no longer in the having to, rob Peter to pay Paul kind of zone in on the systems that they're building in hardware 3.
Right. Well, I have tons more questions on neural networks. I think that's awesome background, but we probably don't need to talk about that all night. So getting to where we're at right now with like the FSD beta, I'd love to get a sense of your sense of the progress, where Tesla's at right now, how far they may have to go, how things are looking, how happy you've been with the progress, those sorts of things. All right, I think that is probably as good a spot as any to leave it for today. So thank you for listening. Make sure to subscribe to stay updated on this conversation and the rest of Tesla Daily. And you can also find me on Twitter at Tesla Podcast. I'll see you next time. Thank you.